We're going to go on TV now. Come on. Hey, all right. Okay, here we are. Welcome, everybody, to the show. See, we got to start with a little monologue. I should start with some jokes, and then we'll go from there. Actually, today, we're going to start on the second section of, I guess, would be topics. The first sort of section of what we've done so far is just kind of methods for differential equations, both using shooting methods and then these direct methods where you just do a Taylor expansion of the problem. Now we're going to move into partial differential equations, and in particular what we're going to concentrate on for a little while here is what are called finite difference methods. Okay. So we're going to spend a lot of time on this and mostly how you solve partial differential equations with this. This is probably one of the most popular methods available, partly because there's actually two reasons. One, you can basically use standard Taylor expansions to do most of the kind of calculations we're going to do in finite difference. And two, you can implement almost any kind of boundary condition fairly easily. Okay? The only restriction that you have is going to be that your domain has to be sort of fairly nice. Rectangular or, or circular, nice geometries. You can't just take any generic domain. We'll talk about really difficult, complicated domains at the very end using finite element methods, but this is a pretty good method. Okay? Now, in particular, we are going to concentrate on talking about the implementation of finite difference methods on what's going to be homework 2. Okay? So this is kind of a precursor for homework 2. So for homework 2, you're going to be solving the following set of equations. So this is what we derived last time in class. We have an equation which couples vorticity to the stream function, where this Poisson bracket operator here is the following: psi dx, d omega dy, minus d psi dy, d omega dx. Okay, so these are the equations we want to talk about solving and talk about using this finite difference implementation. The one last comment I want to make about finite difference. What we're going to find with finite difference is everything's reduced down to matrix algebra. When you discretize the problem using your finite difference methods, everything just comes down to big matrices, huge matrices usually. So one of the very important things that has happened in the development of computational methods is fast ways to dealing with matrix operations. In particular, when you solve things like AX equal to B, things that we don't typically think about. You throw on the computer, you press return, pops an answer. You can do this in MATLAB, Maple, Mathematic. All of them are very fast. We're going to start talking about then coding this thing up where it's not fast. We're going to have to solve AX equal to B thousands of times in a single computation. Then you're asking, how fast can I solve AX equal to B? Because that's going to really be the limiting factor in everything that you do. Okay? So we'll get to that. Last thing here, by the way, I should point out we have boundary conditions as well. So boundary conditions and initial conditions. The initial condition associated with this is typically you give the initial vorticity. At time t equals 0, let's say I know the vorticity distribution in my spatial domain. And for boundary conditions, what we're going to take is periodic boundary conditions. So what that means is the following. What happens on the left edge basically is what's happening on the right edge. What happens on the top is happening at the bottom of our computational domain. So at x equals, we're going to draw the domain. So you have x and y, and so whatever goes through the bottom comes up through the top. Whatever goes to the left or to the right goes through the left. It's going to come out to the right side. Now, you may ask how realistic this is, which is a valid question. And let me just say this about these boundaries. What we're typically going to be doing is solving on some domain and looking at what happens to the vorticity and stream function in this domain. And a lot of what we're going to be doing in the simulation is saying, okay, let's suppose I put some vorticity in here arranged in some fashion. The idea is typically with the periodic boundary conditions, when is this important? Well, this is only going to be important, for instance, if things actually get towards the boundary. Typically, we're going to put some mounds of vorticity in here, watch them evolve. If these are far from the boundary, then the solution out here is tiny. You know, down in the noise level. Remember, the best you can do with accuracy is 10 to the minus 16 places of accuracy. So, frankly, in this domain, if your solution gets pretty small, who cares? There's a little bit of error that's going to come at the boundary. In terms of physically, this is not right? I mean, it's not like on a planet. Well, it kind of is. So if you think about shallow water waves across the planet, what comes over on one side is going to come back around. But you can also think of a section of atmosphere where things coming out here are not necessarily coming back in the other side of the domain. But that's okay. We're not necessarily looking at trying to see what happens if we force things through here. These things are going to evolve and move. And yeah, so if they move here, they're going to pop up over there. Okay? But at least for the purposes of what we care about right now, this is not really that important of a deal. Okay? You can consider other boundary conditions, but this is what we're going to do for this problem in particular. All right, so let's talk about the basic algorithm and talk about what's going to be involved in this. So I'm actually going to do this over here and see how this board works. So we talked about this last time in class. The basic algorithm, we need to solve for both the vorticity and for the stream function. Right? So how do we do that from this equation? Well, first of all, we know that we start off with an initial vorticity. So the way this algorithm works, I know what the initial vorticity is. Great. So if I know the initial vorticity, then I can calculate an initial stream function. So if you're given this, this tells you how to calculate your stream function. I now have my stream function and vorticity at time t equals 0. Once I have this, I have then to solve this equation here. And notice this is now going to be, what we're going to do is turn this into a big ODE for evolving or updating the solution omega, which is our vorticity. Updating the solution, the vorticity in time. So all we have to do is solve this, and what we're going to do is solve this with an ODE solver. We've talked about ODE solvers already. Okay? So we'll now step this forward in time. This gives us our solution for the vorticity delta t into the future. So I've just updated. So I have my stream function. I have my vorticity. This allows me to take a step delta t into the future for the vorticity. Well, once I have the vorticity delta t into the future, I can just make this a loop. Then I can come back, calculate the stream function in the future. I now have the stream function and the vorticity at delta t in the future, which allows me to calculate the vorticity to delta t into the future, and so on and so on and so on. This is your basic algorithm, right there. Okay. So the question is, how do we solve these constitutive parts? I first need to do this, then I need to do this. Okay. So what is the structure that happens with this? And that's what really today's lecture is about. So step one. We have to solve this. And this is an elliptic equation. So how do we do it? And keep in mind that this del squared, Laplacian, so this is really partial derivative with respect to x twice and partial derivative with respect to y twice. Okay. So one of the things we learned from 2 lectures ago, I can't remember, yeah, I think it's 2 lectures ago, is that you have formulas for how to calculate derivatives and first derivatives, second derivatives, third derivatives, and fourth derivatives using this central difference scheme. All you do is you do Taylor expansions. And in fact, it was 2 lectures ago, I think, that you look at the tables. I gave you 3 tables for calculating these kind of things that are ordered to delta x squared accurate or order delta x fourth accurate, forward or backwards difference formulas. And what I'm going to do here is concentrate on saying, okay, let's discretize this. What is the second derivative? Well, if you were to use your Taylor expansions, the second derivative just simply came out to be, now this second derivative in x, what this would come out to be is psi of x plus delta x, y, t, minus 2 psi of x, y, t, plus psi x minus delta x, y, t, all over delta x squared. This is this first piece here. That is a second derivative in x. Second derivative in x, notice it uses its neighbors. Remember, it's using basically a slope formula type thing, where you say, okay, I'm using my point ahead of me in x and behind me in x to calculate the second derivative. And this is accurate to order delta x squared. I can use a similar formula for y, taking a partial with respect to y. So what do I get there? Well, then I get psi of x y plus delta y t minus 2 psi x y t plus psi y minus x y minus delta y t all over delta y squared. That is the approximation to this derivative. So I have this plus this, and that's equal to omega at x, y, t. So that's what happens when you discretize that equation. That's what you get. Notice, this is no longer differential equation, a partial differential equation. This is now a finite, it's a difference equation. Every point here, when you calculate this, relies on neighboring points. Okay? So let's think about it from the perspective of some graph I'm trying to solve for x and y. And what I'm going to do, my domain where I'm going to solve this, let's suppose is something like this. And what do? Well, I'm going to chop this up to a bunch of points and chop this up into a bunch of points. That's the discretization process. Where the distance between these is delta x. So discretize an x. And this is delta y, discretize in y. So remember, when you do computations, you never solve this thing on a continuous interval. You solve it on some computational domain. So if you have a box, you say, I'm going to solve this with a finite number of points. There it is. You chop it up in x, you chop it up in y. Your solution's now at every single one of these points. And notice, if I want to calculate, for instance, here, that point right there, and I want to calculate the second derivative. How do I calculate the second derivative? I mean, if I want to calculate the Laplacian of this, and the second derivative in x and second derivative in y, well, we just talked about it. It's right here. This is the discretization of this. What does it rely on? A point in front in x, a point in back in x. A point in front in y, a point in back in y. I need all those points plus the actual point I'm at to make this work. So if I have this point here and I want to calculate the Laplacian at that point, I need all 5 of those points to calculate this thing. Okay? So you can think about this. This is x plus delta x. This is x minus delta x. This is y plus delta y, y minus delta y. Now, the way I've written it here is a little bit cumbersome to carry out. So what I'm going to do is say, okay, let's let psi of m, n equals psi of x m y n. So I go to the mth point and the nth point. Okay, so this is what this means. So when you come over here, you go over to the nth point here, nth point there, and that gives you your value of psi mn. Or you can think of also omega mn. So this is nothing more than just a discrete counter to tell you how many points over you go this way, how many points you go up that way. That puts you on the points you want, and this is going to be the representation of that. Okay, so that's the counter. The other thing we're going to do here is we're going to say, let's in fact do this in such a way that delta x squared and delta y squared are the same. Now let's consider a box that is square. And let's chop it up in x the same way we chop it up in y. So if x goes from 0 to L and y goes from 0 to L, and we chop them both up into 100 points, delta x squared and delta y squared are going to be the same. Yeah, Pierre.
Y are positive, right? So
Yes, that's correct.
Well, why delta x squared and delta y squared?
Oh, why is it here? No.
So it's just meaning the increments are the same on both axes, right?
That's right.
Delta x equals delta y, right?
That's right. Delta x.
Okay.
Yeah. So yeah. So if you just say delta x is now going to be delta y, that's what we want to do, and we'll let that be delta. So here's going to be my slicing thickness, if you want to think of it that way. Okay. If you've got a Ginsu, that's small. If you go to Benihana's, they can cut that down, way down. Okay? All right? Now, my knives at home are not sharp. This delta's huge. And actually, the interesting thing about delta, by the way, is that delta tells you how fine you do this, right? It also tells you how big a matrix you're going to have to work with. This is going to be very important for what you do, partly because the bigger the matrix you work with, the slower your code. And in particular here, think about if I have a grid like this, and I say, I want to double my resolution. Simple thing to do, which is, if I want to double the resolution, that means I want twice as many points in x and in y. My computation, you would think, would just double. It doesn't. Because, right, if you're doubling the number of, right, it's by 4, excuse me. It goes up by 4 because you're doubling points here by here. You're doubling in each direction. You're getting 4 times the number of points total. And you would say, well, it's cost me 4 times as much work. No, actually it doesn't. Partly because what we're going to find is when we solve this here, when we try to solve this for this problem here, the computational cost for doing this goes like the number of points cubed. So if I do this and I go up by a factor of 4, really I'm going up by a factor of, not the same 4, but 4 cubed. Okay? So this is something that's really crucial, is computational cost for doing all this. And this is one of the things you'll investigate when you do this thing. Okay? All right. So let's talk about that equation a little bit more now. With this assumption, notice the following thing. I have delta x equal delta y, delta. So I can multiply this delta x squared the same as this delta y squared. I can multiply both sides of the equation by delta squared. And what I end up getting then is this thing comes out here, this thing comes out there, and I get a this times delta squared. And notice, how many points, so what's the weight of the point at xy? Well, I have minus 2 of them here, minus 2 of them there. So there's a total of minus 4 of them. And then there's 1 of each of the neighboring points. So in total, I can write this set of equations that comes from discretization as the following. I have minus 4 psi mn plus psi m minus 1 n plus psi m plus 1 n plus psi m n minus 1 plus psi m n plus 1 is equal to delta squared omega m n. This is the short way to write that set of equations. Okay? And we have boundary conditions to go with this. periodic. So what periodic boundary conditions mean is that this point over here, this whole line, should be identical to this line over here. So if I have the solution here, I know what the solution is there. So what we're going to do is chop this into a total of n plus 1 points. So this is, you can think of 1, 2, 3, all the way up to, this is n plus 1. You don't need to solve for n plus 1, because it's the same as 1. That's what periodic means. Same thing in the y direction. You start 1, 2, 3, 4, all up to n plus 1. This is identical to this, so really you only have to solve for 1 to n. Okay, so given that, let's ask about a boundary condition. So for instance, if you're over here, this point here, and I want to calculate the Plossian, it relies on what? The neighboring points, right? It relies on this neighbor, this neighbor, this neighbor, and this neighbor over here. What is this neighbor over here? Well, you have to think about that since this is the same as this, it's like essentially like being here, it's that guy or girl. You don't know. Okay? So you see, this is how the boundary condition works. Same thing if you're down here, relies on this, 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 and that one. So stuff here sees things up here, things over here, see things over here, and same thing here. This point here relies on here, 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 and this one, which is the same as that one. Okay? So then you have the following boundary conditions. So remember, m is how far over you are here. N is how you're going up this way. So psi of 1n is equal to psi of and psi of all this says, if you are in this first m, this is equivalent to being on this one here. That's what this says. This says if you are on m1, in other words, n is 1 here. If you're on here, it's equivalent to being on here. Okay, these are the periodic boundary conditions. So in some sense, we've reduced this problem under discretization to this set of equations here. Now, the big step comes next, which is, okay, you have this set of equations. My claim is this is nothing more than linear system of equations, ax equal to b. What is a, what is x, what is b? That's what you've got to figure out. And this is where it takes a little bit of, you go home, you work it out, you do it with pen and paper, because this step here is really a very important step, and you have to convince yourself this is actually right. Okay? What am I trying to solve for? So we can talk about that first. I'm trying to solve for x. If you solve ax equal to b, x is the unknown. Well, what is the unknown here? I'm trying to solve for psi, the stream function. And it is related to something I know, which is the b vector. The thing I know is the vorticity. So all the matrix A has to tell me is how all these coefficients are changing. All right? So let's come back over to here. This is kind of where you need a big board. But we'll do with what we've got. And in particular, I'm going to consider a system where n equals 4. Yeah, Pierre.
We know that vorticity only at t equals 0, right?
Right. So right now we're just trying to solve for the stream function at t equals 0. And then, once we have both of those, then we can step them forward in time. Okay? So let's start with the n equal 4 case. Let's write down the first few of these equations. So if you have n equal 4, I want to write down what some of these equations look like. What does this equation represent? Well, let's go back and look at it. Here, this is when n and m are both 1. So really, it's looking at right here, at that point right there. So maybe I should just draw this over here. So n is 4, so we've basically 1, 2, 3, 4, and this fifth thing, that's n plus 1, this is the same as the first. So I have 1, 2, 3, oops, sorry. Four, and then that's my 5, but 5 is equal to 1, right? And then here in this direction I have 1, 2, 3, 4, and 5. So for this equation, which I just got directly from that by putting, so that one there, I just said, look, n is equal to 1, m is equal to 1. And I put it into the equations over there. And basically, it's trying to update the solution at that point. And what does it rely on? Well, it relies on -4 at that point, plus it relies on 1 here, which is, this is psi, go over 1 up to, that's that one, plus this point here, which is psi 2, 1. Is that one there? So you could see that these are kind of like x and y coordinates, right, for where you are in this grid. And then a point here and a point there. But what are those points? Well, this point really is that one there, right? Because this point is equivalent to this one, so it's seeing essentially that point. Well, what is that point? Well, that's 4, 1, right? And then this point here is really that point there. It's 1, 4. Okay? Then you go up a point and say, okay, I just evaluated that equation. Now, let's go up and find the solution here at 1, 2. Then it relies on, let me write it down and then we can, so what does this point rely on? It relies on this one, this one, this one, and over here, which is that one. So there's -4 of that point. This point here is 1, 1. This point here is 2, 1. Oops, 2, 2, excuse me, because over 2, up 2. This point here is 1, 3. And then this point over here, which is 4, 2. And you just basically go up and you do it for every single one of these points on your domain. How many points total are there? Well, there's 4 this way you have to solve for, 4 this way, a total of 16 points I have to update the solution for. So I get 16 equations here. 16 equations, 16 unknowns. And let me tell you that that then turns into AX, well, let's call it the next. Now let's call it more specifically. A psi is equal to delta squared vector omega. Let me tell you what these vectors and matrices are and see, and we can talk about where they come from. So first of all, the vector psi is the collection of things I'm trying to solve for. Now, for lack of a better way to do this, this is just the way I've ordered them here. I said, okay, let's collect all these things. So I have to solve for all these. And notice I was going up this way, then over here, then over here, then over here. So this is going to be psi 1, 1, psi 1, 2, psi 1, 3, psi 1, 4. Once I get to here, I come back down. Because this point's already that one. So I solve for those 4 points. And the next one, psi 2, 1, psi 2, 2, all the way down. I guess I could write the whole thing out. It's not that big. There's 16 components. Psi 2, 3, psi 2, 4, psi 3, 1, psi 3, 2, psi 3, 3, psi 3, 4, psi 4, 1. psi 4, 2, psi 4, 3, psi 4, 4. Get crunched at the end. It is equation 2114a in the notes. Okay. 16 components. These give me all these points. Omega is the corresponding vorticity values at these points. So omega 1, 1, omega 1, 2, omega 1, 3, omega 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. Okay? Obviously, you're going to have the computer animate this for you, because we're not going to do simple 4x4s. We're going to maybe do, 60 by 60s. Okay? But what size vectors then are you going to work with? This is the important thing. Whatever you discretize here and here, think about this. Suppose I slice it to 100 points this way, 100 points this way. So if n is 100, then how big are these? 100 squared. Okay? That's a pretty big vector you're working with, right? So you're now then looking at working with a 10,000, a vector that's 10,000 by 1. So already you start seeing the computational cost, right? Because now you're saying, I'm not working with small matrices, because now the matrix A, how big is this? Matrix A right here is 16 by 16. And what does it look like? And by the way, that matrix A, if I did do 100 by 100, is a 10,000 by 10,000 matrix. So now you're going to say, I've got to solve AX equal to B with a 10,000 by 10,000 matrix. And believe me, 100 points in each direction is not much. Okay? If you're doing a simulation of airflow over a wing and you're using these kind of equations, you're using a lot more than 100 points. You're going to be using thousands of points. Now, thousands of points squared. That's the size of the matrix you're working with. Okay? So you're going to work with matrices that are million by million or more. You need a fast way to solve that. Okay? All right. So let's talk about this matrix A. And understanding this matrix A is very important because we're going to have to do a lot with it in the homework. And we'll spend some more time in lectures with it. But let me show you what it looks like. 2, 3. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And there's a 1 right there. Okay. So for instance, that's the first row. Does it make sense? I'm taking this matrix and multiplying this matrix by this vector. So let's take this vector, think about laying it right on top of that, and in fact, see if it reproduces this equation here. So you take this thing, lay it over here. Well, this -4 multiplies psi 1, 1. Well, I do have -4 psi 1, 1s. That's good. Then I have 1 times psi 1, 2. I have one of those over there, too. 0 that, and then I have 1 times psi 1, 4. Psi 1, 4. This next component is multiplying psi 2, 1. Right? Because it goes psi 1, 1, psi 1, 2, psi 1, 2, psi 1, 4, psi 2, 1, psi 2, 2. So psi 2, 1, which I have. And then nothing until I get to here. And this is psi. So this is psi 1, 1, 2, 3, 4. Psi 2, 1, 2, 3, 4. Psi 3, 1, 2, 3, 4. Psi 4, 1. Psi 4, 1 is right there. So indeed, this thing here reproduces that first equation. And in fact, the chain of equations you write down there then reproduce the following structure. And then I got a bunch of zeros. You get that? Okay. And then next one is, let's see, Yeah, and then 0, 0, 1, 0, and so forth. So now here's the structure that you start seeing. And then the next one down is important, actually. 1, 0, 1, negative 4. 0, 0, 0, 1. And then 0, 0, 0, 0. 0, 0, 0, 1. So for instance, here's the first set of 4 equations. Now what you're going to see is, here's the structure of the rest of the matrix. See this little submatrix in here? You see this 1 that was here gets popped over to here, and then the 1 that would be over here is popped over here. That's due to boundary conditions, periodic boundaries. This structure here, let's call it Q. Where each one of these dotted areas represents a 4 by 4 matrix. Q comes down like this. So that structure gets repeated down like this. Here, that's the identity matrix. That identity matrix comes down here, comes down here. This identity matrix comes down over here. Actually, excuse me, that's not right. No, this is right. Yeah, so hold on. 0 matrix, 0 matrix, 0 matrix. This is the mess you get. I wrote the whole thing out there in equation 2.113 in your notes. But you see that this Q matrix gets repeated down the diagonal. The identity matrix gets repeated down the diagonal. Over here, it should be over here as a boundary, but the boundary periodic boundary puts it then over here. And then you also get it on the off diagonal, and instead of getting it there, it gets repeated over here due to periodic boundary conditions. Okay? This matrix, my claim is, if you take this matrix A, which is a 16 by 16, you multiply it by the psi, it's equal to omega. This reproduces all these set of equations. How do you solve this in MATLAB? Well, it's really easy. You just take this equation, say psi is equal to A backslash this thing here. Let's call that omega. I'll incorporate the delta squared into it. And there you go. That's your solution. Solves a 16 by 16. Okay? Now, there's one way to solve it. Generically, if you do this kind of stuff, what happens over here, generically, is if you do this command in MATLAB, it's going to cost you order n cubed operations. Okay? It's usually a sort of a, it does a Gaussian elimination, then LU decomposition. The point of here is n cubed. So, you can ask the following question. If I take my code right here, and remember, this is only a 4 by 4 problem. Suppose I wanted to double the resolution. So in other words, I double the number of points in x, I double the number of points in y. So essentially now, instead of this vector being, instead of 4 by 4, now it's going to be 8 by 8, which is 64, right? So essentially what I've done is I've taken this up by a factor of 4. Well, if you take this up by a factor of 4, this goes up by a factor of 4 cubed. The computation time does. Okay? So you can start seeing that if you increase your computational domain or you want to get better resolution, this thing is going like this thing is really increasing very rapidly in terms of the number of operations you've got to do here. And again, take it to the case of I have a 1,000 by 1,000 matrix. I want to double its resolution. You know, that's a significant cost to what you've got to do to compute this thing. Okay? We're going to try to stay under 100 by 100 matrices, just simply because most of you are going to be working on desktops or machines. That's going to take plenty of time in and of itself. Okay? Otherwise, if you really want to go to high resolution, you should put it on as a background job, let it sit overnight or 2 days or 3 days, then come back and look at the results. Okay? All right, so this is costly. And in fact, this is the slowest part of the code, doing this operation right here. So we need to find ways to do this quickly. one of the things that you'll see if you've looked at the homework 2, which hopefully you probably haven't so far, you just concentrate on homework 1. But eventually when we're going to concentrate on homework 2, we'll talk a lot about this, is how do you solve this very quickly. As a parenthetical remark, solving this quickly, about a year ago, 2 years ago, maybe even 3 years ago, I don't know how, they put out the top 10 algorithms of the last century. Okay? Computers were invented in the last century, so they said, okay, what are the top 10 algorithms that have been invented? 4 of them had directly to do with how to solve this fast or quickly, because this is almost going to be your hang-up every single time. So order n cubed, people can do pretty much state-of-the-art n log n. It's about as fast as you can go. And the algorithms that can do this, all named top 10 algorithms of the current century. Okay? Significant savings, because log n is almost linear. This is almost constant. It's really close to being n. You scale it, you double the size of your problem, you only double the size of the computation, instead of making it 8 times bigger, for instance. Okay? That's huge savings. So if you can ever write an algorithm that does this, you got yourself a top 10 algorithm of the next century. Okay? There's no way you can really beat that. Just order n. So, but if you can take this log n down off of there, you're still a winner. Okay? All right. So this is how you generate this structure. Turns the problem from being what it was, which was a simple, let's come back to here, partial differential equation in x and y, continuous. You chopped up your domain. This turns out to be a bunch of linear algebra. A huge amount. Big deal. It's ax equal to b. This is what MATLAB's built for. So you can solve it. Now the question is, now once I do this, I can solve the stream function. Now, what about this? Okay. So what about that? Let's take care of that now. All right. So we will also talk about how to build that matrix A. Well, don't worry, we're going to spend a lot more time about this. This is mostly the warm-up to what we're really going to be doing for this second problem, second homework, which is going to be a lot of the next lectures in the next few weeks. Okay. Now let's talk about the other problem. Assuming that I can calculate this thing nicely, which we just developed sort of a way to do this, now I want to solve for the vorticity, updated in time. Well, you can do the same kind of thing you did before, which is, hey, these are just derivatives, right? I mean, I can, if I rewrite this in terms of, I'm going to move this to the other side, this simply becomes that. Okay? But what do we know about derivatives? I can just use my central difference formulas, right? So you can do this whole thing that we just did previously. I can expand this out. It's only a y derivative. This is an x derivative. This central difference in x, central difference in x, central difference in y. I already know what this does. What did the A matrix fundamentally do? The A matrix fundamentally gave me what this does. That finite difference discretization essentially said this thing here turns into that. So if I see this Laplacian operator, which is 2 derivatives in x, 2 derivatives in y, I know basically if I multiply by this matrix A, I can take 2 derivatives in x and 2 derivatives in y. So when I come back over to here, I look at this thing and say, I want to discretize this thing. Now I want to discretize it and look at all points. What's this? That matrix A takes 2 derivatives in x, 2 derivatives in y. That's what we just showed. Plus there was this factor of delta squared over the bottom, right? So you still need that around. That was our delta x, delta y. So that's easy. Now, the thing is, these are just as easy. In fact, these are easier than what we did here. I can just say, what is it? How do I discretize one derivative in y? Okay, so what I can say is, why don't we let the matrix B do that? I can calculate a matrix B that will discretize this thing just one derivative in x. You just do exactly what we did before. You discretize an x, you go through and you calculate, what is this matrix that I multiply this by that gives me this finite difference relationship? You know, I get some set of equations that look something like this. They're different because it's only one derivative in x, but fine. From this, I constructed a matrix A that was effectively this thing. I can do the same thing for matrix B. And let's talk about then matrix C maybe as a y derivative. Then what does this problem boil down to? Well, this comes to this. Then I say, okay, well, decide dy. Well, the y derivative is this. Is that d omega dx? Well, there's the x derivative. Oops, one of these should be a plus sign. That one. And then you have this here, psi dx, which is b psi c omega. So under discretization, and in fact in your homework, you're going to have to find out what c and b are. Okay? So you find out what c and b are. You already know what a is. I gave it to you already. All you do is say, now notice, this is now a differential equation. There's no partial differential equation anymore. I discretized in space, in x and y. So now all this is how do all these points evolve in time? And here's the interesting thing. Essentially what you're doing now is saying, okay, I want to solve this thing in time for my x and y values. So I start off at t equals 0, and I discretize in space and time. And what I want to do, this is at t equals 0, and I want to move up to delta t in the future. Well, in delta t, I still have these same points. How do I get a point delta t into the future? Well, it turns out any point in the future, if you take its corresponding point in the past, if we just think about this way, notice that, for instance, what does the A matrix do? The A matrix tells me that, in fact, I rely on my neighboring points. So my solution in the future at a certain point relies on neighboring points. And you're going to find the same thing for C and B. So in fact, my solution in the future, delta t, relies on these 5 points. These 5 points give me an updated value of the vorticity at that point in space. And I can go through and then update every single point here at time delta t. And how you go from here to here is using a standard differential equation solver like OD45, OD23, all built in. The same thing you're using for doing homework 1. The only difference is, here's your right-hand side. Once you write your matrix A, B, and C, your right-hand side is actually really easy to calculate. There it is. This is the only thing you've got. In fact, the right-hand side of this thing is like the easiest thing to calculate. You calculate it, and this is essentially what it's doing. Take these 5 points, and with these 5 points, you update your whole future at delta t, and then you say, okay, now I've done that. Now update delta t to delta t, and you keep this process going. Every time you do this, when you get this updated solution, you have to go back, though, and solve for the new stream function. So notice the operation count. From here to here, when you solve it this way, notice you don't have, with A, B, C, all you're doing is matrix multiplication, which is a fairly straightforward operation. But every time you update it, where the cost comes in, you say, I've updated the solution, delta t into the future, but now my stream function has to be updated, and I've got to do that much work to get my new stream function. Once I get it, then I can come back, multiply this, that. Okay? And you step up your solution in the future. So really what today's lecture is all about is outlining some of the basic ideas of discretization, trying to point out to you, in fact, that what's going on here is exactly what you're going to be working on in the homework. This is the kind of setup we want to do. And one of the big problems we want to think about doing, and this is what we're going to really spend a lot of time in second homework, is what are some different alternative ways to solve this problem right here? And do it quickly. Okay? That's it for today. See you guys Friday. Office hours today, by the way. 2 to 3:30. Please feel free to come by. I'm there to help. I'm your pal.